For more than 100 years, our entire picture of the cosmos has been held together by two giant ideas. The problem is, they don't agree with each other. And now, new data coming in from the very edges of space and time is starting to show the cracks. So today, we're going to dive into a real, fundamental crisis in physics, a moment where our most basic understanding of gravity, and maybe even reality itself, is on the line.
And let's just start right here with this quote, because it absolutely nails the stakes. This is not some small academic squabble. Dan Skolnick, a cosmologist at Duke University, puts it bluntly. The tension has turned into a full-blown crisis. That's a huge deal. It means our standard, trusted model of how the universe works is probably broken. So what is this crisis, really? Well, it all goes back to a problem that's been bugging physicists for a century. We have these two pillars of modern physics, general relativity and quantum mechanics, and they're just incompatible. It's like they describe reality in two completely different languages. And for a long time, we could kind of ignore that. But now, the universe itself is sending us data that forces us to finally deal with it.
Okay, so on one side, you've got Einstein's masterpiece, general relativity. It is beautiful. It describes the universe of the very, very large planets, stars, galaxies, the whole show, by treating gravity as this smooth, elegant curvature of space-time. And honestly, it has passed every single test we've ever thrown at it. Well, until now.
Then, on the other side, you have quantum mechanics. This is the rulebook for the world of the very, very small, and it describes this bizarre, kind of pixelated reality of particles and probabilities, where everything comes in these little discrete packets, or quanta. It's unbelievably successful, but its description of how forces work just totally falls apart when you try to apply it to gravity. So this theoretical conflict has been simmering in the background for decades, right? But now, it's officially boiled over, and that's thanks to two major pieces of evidence from our telescopes that just don't fit the models we have. It seriously feels like we're looking at two different universes. Problem number one is something called the Hubble tension, and it boils down to what should be a simple question: how fast is the universe expanding? But we get two different answers. When we look deep into the past, at the fossil light left over from the Big Bang, we get one speed. But when we measure the expansion using stars and galaxies right here in our cosmic neighborhood, we get a totally different speed.
And this graph, wow, it just lays the problem bare. On the one hand, measurements from the early universe suggest the expansion rate is about 67 kilometers per second per megaparsec. On the other, local measurements are giving us a value closer to 73. And for years, scientists were like, okay, maybe the error bars will eventually overlap as we get better data. Well, they didn't. They don't. This disagreement is real, it's statistically significant, and it's a huge problem. And if that wasn't a big enough headache, the James Webb Space Telescope went and found another one. It peered back to the very dawn of the cosmos and found galaxies. But not just any galaxies. It found galaxies that were way too big, way too bright, and far too complex for how old they were supposed to be. Our standard model says there's no way they should have had enough time to get that massive, that quickly. And this table really shows you just how radical the potential solutions have to be. To explain those weirdly big early galaxies, some physicists, like Rajendra Gupta, are saying, hey, what if the universe is actually twice as old as we think it is? We're talking 26.7 billion years instead of 13.8 billion. In a model like that, things like dark matter and dark energy aren't even real substances. They're just illusions, caused by the fundamental constants of nature actually changing over time. I mean, that is a profound challenge to literally everything we thought we knew.
So, faced with this massive crisis, physicists are basically taking two different paths forward. The first path is, let's say, the more conservative one. It says our theory isn't totally wrong, it's just incomplete. We're just missing a piece of the puzzle, a new particle. And if we can find it, we can finally unify physics.
And that missing puzzle piece has a name: the graviton. It's the hypothetical quantum particle of gravity. If this thing exists, it's the key to everything. It would finally prove that gravity, just like all the other forces, plays by the weird rules of quantum mechanics. The problem? For decades, actually detecting a single graviton was thought to be completely, fundamentally impossible. But then, everything changed. A huge theoretical breakthrough in 2024 showed that with some of the incredible new quantum tech we have, detecting a graviton might actually be possible after all. What was once just a dream for theorists is now a real, tangible, experimental goal. So how in the world are they going to do it? Well, the idea is just brilliant. You start with a powerful gravitational wave, say from two black holes merging.
When that wave passes through a special detector, a resonator made of superfluid helium is designed to absorb exactly one quantum of that energy, a single graviton. That tiny energy absorption creates a discrete little vibration, something called a phonon. That phonon causes a detectable quantum jump in the resonator's energy, which ultra-sensitive lasers can then pick up. They're trying to see the individual pixels of gravity itself. It's amazing.
Okay, but finding the graviton is only path A. Path B is way more radical. This one says, forget about finding new particles. It suggests that we need to throw out the old rulebook and completely rewrite the laws of gravity from the ground up.
This path kicks off with a really mind-bending question. What if gravity isn't a fundamental force that's actually pulling things together? What if it's something else entirely? To get your head around this, think about temperature. Temperature isn't some fundamental thing, it's an emergent property. It's what you get from the collective jiggling of countless tiny atoms. You can't ask about the temperature of a single atom, right? The concept doesn't even make sense. So what if gravity is like that? An illusion that emerges from something much deeper going on underneath.
And that is the core idea behind a wild theory called entropic gravity. It proposes that gravity isn't fundamental at all. It actually emerges from the principles of information and, believe it or not, thermodynamics. Specifically, it's driven by the universe's absolute relentless tendency to get more and more disordered, to increase its entropy. So here's how it works. In the framework laid out by physicist Ginestra Bianconi, you can think of dense matter, like a star, as this highly organized, low-entropy island of information. This creates what she calls an information mismatch, with the much more disordered, high-entropy empty space around it. And gravity? Gravity is just what space-time does to fix that mismatch. It curves in a way that maximizes the total entropy of the whole system. Now, the ambition here is just breathtaking. This isn't just about explaining gravity anymore. This is a serious attempt to build a whole new foundation for physics by unifying general relativity, quantum mechanics, and thermodynamics, all under the single, powerful umbrella of information theory.
So, that's where we are. Cosmology is standing at a profound crossroads. This crisis isn't an endpoint, it's a branching path. It's forcing physicists to make a choice that will lead them into a completely unknown future.
So which path will it be? Is it the path of discovery, where we hunt for the graviton to finally complete our particle-based picture of how reality works? Or is it the path of revolution, where we rewrite gravity entirely as an emergent property of information and entropy?
Nobel laureate Adam Rees, one of the people who discovered that the universe's expansion is accelerating, he just sums it up perfectly. The universe isn't giving up its secrets easily. Nature is making us work harder. This isn't some simple puzzle. It's a deep, deep mystery that's forcing us to question our most fundamental assumptions about everything. And that is exactly why this moment is so incredibly thrilling. The revolution, whichever path we go down, is going to fundamentally reshape our entire conception of the cosmos. This isn't just an update for a physics textbook, it's a paradigm shift. We are literally watching a scientific revolution happen in real time.
Which really leaves us with the ultimate question. Is reality built from the bottom up, out of fundamental particles and forces? Or is the universe something else entirely? An emergent, macroscopic story that's written in the language of quantum information? The answer is out there, just waiting for us to find it.